Hello everybody. In this video, we are going to practice using our flowchart to kind of help us launch us in the correct direction for analyzing this problem. Let's go ahead and give it a shot. So it says Clearwave Water Solutions, the company known for its residential filtration systems, has recently unveiled the AquaPure 3000, claiming it can eliminate harmful bacteria in the household water at a dramatically improved rate over its older model, the AquaPure 2000. To prove its claims, the company launched a 6-month field study tracking bacterial contamination in homes using either the AquaPure 2000 or 3000. For each home, engineers tested whether water samples were free of bacterial contamination after 1 month of filter use. The study results: AquaPure 2000 group. 220 homes tested, 185 had bacteria-free water after 1 month with an average bacterial load of those infected at 5.5 colony-forming units, CFU, per milliliter. AquaPure 2000 group, 210 homes tested, 21 homes had bacteria in their water 1 month with a average load of 6 CFU per milliliters. CEO Lana Patel wants to know if there's statistical evidence that the AquaPure 3000 outperforms the 2000 model in delivering bacteria-free water. She asked the analytics team to conduct a hypothesis test at the 5% significance level. Okay, so we've got a whole bunch of things going on here. We have kind of a big setup. In here, there's only a couple of things that are actually really important. At the end here, we know that we're trying to do a hypothesis test. And so far, the hypothesis testing methods that we have learned are really things like one sample hypothesis testing, two sample hypothesis testing, and regression. So we can kind of start working off there. So maybe our first question should be, how many groups are we dealing with? Are we dealing with one group, or are we dealing with two groups? Or are we dealing with kind of regression where we're dealing with multiple numerical measurements of the same thing and using one to predict another? So kind of clearly here, we've got two different groups that we are comparing one to another. These two filters, or these filtration systems, the AquaPure 3000 and the AquaPure 2000. So kind of right away, I know that I'm dealing with two sample hypothesis testing. And from the flowcharts that we've been doing, we have one that's labeled with two sample hypothesis testing. So we should probably start off here. Our first question says that, we need to identify our data type, and we're going to go and look at our output and some of our calculations as well to see if the problem itself can give us some help on what type of data are we dealing with. So if we scroll on down to our outputs, notice that we have one that is a z-test of proportions of two samples, and here we have a t-test of a two sample of equal means. So it looks like that they've kind of given us a misdirection here. They have one that's proportion and one that's mean, so we can't really use that to help us out. But if we scroll down a little further, sometimes you can look at your answers. And if we look here, let me delete this out real quick. If we look here, we have in our null and alternative hypothesis, we have a really nice help here. Notice how all of these hypotheses have pi in them. And when we're dealing with pi in step one, when we're identifying our data type, it knows that we're dealing with categorical or difference in true proportions. And so we have group one and group two. Group one was the AquaPure 2000, and group two was the AquaPure 3000. Awesome. That gives us a lot of help up here to know what type of hypothesis tests we're doing. We're doing categorical difference of true proportions. So we can look at our populations. The two groups that we're dealing with, 1 and 2, are AquaPure 2000 and AquaPure 3000. And that's in step 2, just looking at the populations. And the parameter is, what are we looking to compare? Are we looking to compare a true mean between the two groups or a true proportion? So we kind of got to look at what they are giving us and seeing what are they asking about their question, because they've actually given us kind of some numerical data and some categorical. Let's look at our at the scenario first. So it says we have a sample size of the AquaPure of 220 homes. And in there, we asked them, like, are you bacteria free or not? And here we said that 185 homes had bacteria free water. That's a classic way that we can get categorical data, where it tells us the number of like successes that we have, which would be this 185 bacteria free homes. And then we also get a piece of numerical data. Look, it says that bacteria-free water after 1 month of use with an average bacterial load at 5.5 colony-forming units per milliliter. So they gave us an X bar too of this 5.5 like colony-forming units. So we need to know, it's like, in this scenario, are we interested in comparing like the proportion of homes that are bacteria-free, Or are we interested in comparing the houses that had bacteria, their average colony forming units? And are we going to look at it that way? So here, when it says that Lana Patel wants to know if there's statistical evidence that the AquaPure 3000 outperforms in delivering what? Bacteria-free water. Okay, so we know that we're interested and we can key off of that categorical data. So when we look at our hypotheses, we know that we're dealing with proportions, and we know that we're going to have pi 1 minus pi 2, and we've got to figure out our inequality over here. Let's zoom in just a little bit. And we know that the inequality here in the alternative hypothesis is established in this scenario, and the null hypothesis is always the opposite of what the alternative hypothesis is. So let's go ahead and see. We want the statistical evidence that the AquaPure 3000 is outperforming. We have to think about, okay, what does outperforming mean in here? Because sometimes outperforming could mean a bigger value, and sometimes outperforming could mean a smaller value. So we want to know the proportions of homes that are bacteria-free. And for us to be outperforming, we want more and more and more homes that are bacteria-free. So that means that we want AquaPure 3000 to have a higher proportion than the AquaPure 2000 of bacteria-free households. Okay, so if we come down here, we see that AquaPure 2000 is our group 1. So I'm just going to write that up here. AquaPure 2000 we want as group 1. And we want as group 2 the AquaPure 3000. Now we have to say, if we want them to outperform, that means we want like a large proportion, let's say 90% of homes here, and let's do 70% of homes that are bacteria-free. I'm just making these numbers up right now so that I can think through which direction do I want. I know it's not equals because I know I need a direction. I think AquaPure is doing better than the 2000. I just need to know, is it going to be a greater than symbol or is it going to be a less than symbol? Notice that we have AquaPure 2000 as first. So I'm going to put in this kind of made up value that I did, this 70% for the AquaPure 2000. I'm going to subtract from it what I think is better for the AquaPure 3000. And that equals negative 0.2. Okay, notice how I have this set up. If AquaPure 3000 is better than the 2000 and we subtract them from each other, I get a negative number. So I think that this letter C is the correct approach. I'll highlight that yellow. Great, so we got our hypotheses done, and that helped us out in step 3. Let's go. What type of test should Lana's team use? All right, that is looking at step 5. Let's kind of zoom in here on our step 5. And we see that the first question is, okay, in the 2-sample testing, are we dealing with means or proportions? It says, oh, we're dealing with proportions because we are looking at pi in our hypotheses. So we know that we're doing a 2-sample z-test of proportion. So 1 sample, wrong. Chi-squared, haven't covered it yet. 2 proportion z-test, that is exactly what we are looking for, and we can highlight that one. Excellent. Next is it saying, okay, what are the observed sample proportions for the 2 groups? So it's just wanting us to calculate, okay, group proportion 1, group proportion 2. Let's go ahead and calculate them out. And we can look and see that there is a kind of common misdirection in here that we can look at as well. So this is the AquaPure 2000 and 3000. I'm just going to go ahead and label these AquaPure, 2000. And we'll do AquaPure 3000. And let's see what they give us. We'll give us bacteria-free. We'll do the next one as with bacteria. And we'll do a sample size. And we'll then ask for the proportion. Sorry. There we go, proportion. So in the AquaPure 2000 group, it said the first thing it said that they had 220 homes that were tested, 185 were bacteria-free, 185. This thing about the colony forming units, this load, is inconsequential for this hypothesis test. Okay, so we've got those. And if we want to know the number with bacteria, we can just do equals 220 minus 185. And now we have the number of successes and failures in our AquaPure 2000. Let's do our AquaPure 3000. So it said 210 homes, but notice how it said it gives us 21 homes with bacteria. One common thing is that we can get going fast and we can just say it's like, oh, it gave us both of the successes. And well, it's like, wait a second. One is talking about being bacteria free and one is saying like with bacteria. So we need to make sure that we are comparing the same direction for both, that we're comparing the successes with successes or the failures with the failures. And we need to kind of read the problem to see which one are we interested in. Okay, so I'm going to do 220 or 210 minus this 21, and it gives us our 10. And now we're looking at like, okay, what proportion are we testing? So let's look at our problem, because we could do it either direction. We just need to know which direction is the correct way to look. So it says Lana Patel wants to know if there's statistical evidence that the AquaPure 3000 outperforms the 2000 in delivering what? Bacteria-free water. This is kind of our key indicator right there. Okay, so we want to know the proportion of bacteria-free. So for the AP 2000, we're going to do bacteria-free divided by the sample size. And for this one, we're going to do equals bacteria-free. Oopsies, that one is incorrect. Let's come in here. We divided instead of subtracted. Here we go. Subtracted. There we go. We do equals 189 divided by 210. And we've got our two proportions. So the proportion for group 1 is like 84. The proportion for group 2 is like 90. Let's see if we can find one down there that matches up. So our first one, it looks like that we got it. 84% for group 1 and 90% for group 2. 85 divided by 220, 89 divided by 210. That one looks great. I'm going to highlight this one. This next one, though, is the common one that is chosen oftentimes in error because we just get going fast and we're like, oh, group 1, it said 85 divided by 220. And the second one was just like 21 divided by 210 because it was just what was given. Don't go too fast. Make sure that you know which we want to use. All right, let's keep on going down. What type of study is this? So this question in our flowchart is just kind of talking about like, okay, do we have like a true experiment? Do we have like a quasi experiment? Or do we have just an observational study? So the key thing here, the first question that we need to ask is, do we manipulate the treatment? That means it's like, do we randomly gather a bunch of homes and we tell them like, hey, we are going to give you the AquaPure 2000 or the AquaPure 3000. Like, we are going to make you do this. Or do we just say, what are you using and do you have bacteria? That's kind of the observational side. So let's see what's going on here. In our problem, we can see that how do they have the homes? How do they gather them? So here we say, to prove its claim, the company launched a 6-month field study tracking bacterial contamination in homes using either the AquaPure 2000 or 3000. From this sentence, it does not appear that we are manipulating the treatment, like we are telling them what to do or that we are randomly assigning. It just says that we are observing what is going on. Because of that, this is a non-experiment or an observational study. We're not manipulating what's going on. We're just asking what's happening. So, non-experiment. Question 5, which of the best follows a type 2 error? All right, type 2 errors, we have a nice table for this in step 4 of our chart, where we have type 1 errors are where we reject the null hypothesis. That's what the data tells us to do, but the null hypothesis is correct. And a type 2 error, what we're interested in is when we fail to reject the null hypothesis, when the null hypothesis is incorrect. Let's go ahead and look at our hypotheses that we set up real quick. So a type 2 error says that, hey, we are going to fail to reject the null hypothesis, which means that we do not show that AquaPure 3000 is better than the AquaPure 2000, but in reality, the AquaPure 3000 is outperforming. So let's go take a look and see what we've got. Question 8, concluding the AquaPure 3000 is more effective when it is not. That is textbook type 1 error. We rejected the null hypothesis that the two groups are the same. So we claim that the AquaPure 3000 is more effective when it is not. So that's not what we want because we're looking for a type 2 error. Type 2, let's look at this one. Concluding that there is no difference with when the Aqua Pure 3000 is actually more effective. That is what a type 2 error is. We got that one. So let's highlight this. The other two are just extra spots. Using a two-tailed test instead of one-tailed, that's not a type 1. It is a problem, but it's not a type 1 or type 2 error. Or failing to use the pooled proportion, this test statistic, again, issue, but not a type 1, type 2 error. Let's go down and look at our last question. So from the output, what is the statistical conclusion? So from the output, we need to see what we're going to do. We know that our alpha level is stated up in the problem at the 5% level of significance. And so when we do our statistical tests, we can compare our p-value to our alpha. So let's look at our p-value then. And we have to decide, are we dealing with a one-tailed or two-tailed? Well, our null hypothesis, let's just scroll down real quick, had a less than symbol. And if you forget about which one is one-tailed or two-tailed, you can always come up to step 3 in your flowchart when we're setting up the hypotheses, where it says right here that it's a one-tailed test if either the alternative hypothesis or is either greater than or less than, and we had a less than, we had a less than symbol in there. Okay, so we know that we're dealing one-tailed, so our p-value is really small compared to our alpha, so we are going to reject the null hypothesis. Now remember, there are some other ways that we can reject the null hypothesis as well. Let's go take a look at, at an alternate methodology. So down again in step 9, we can see that we could also compare if the test statistic is larger than the critical. Like, hey, I think we can calculate criticals. I think that that is provided to us in one of our steps. Let's go see where we're at. Okay, so we could calculate it in here, but we actually, it's not given to us, and in two-sample hypothesis testing, we probably won't have to do it. In one sample hypothesis testing, we could, but we could compare this z statistic to a critical value. But the easiest way from this output is just comparing the alpha level to our p-value. Okay, let's go down and look at our possible options. So we do want to reject. And so are we going to reject and say there is significant evidence that the Aqua Pure 3000 is more effective, or reject and say that there's evidence that the Aqua Pure 3000 is less effective? And we had it set up so that our alternative hypothesis was suggesting that the Aqua Pure 3000 is more effective. And so we are rejecting and making that claim that the Aqua Pure 3000 is in fact more effective. So anyhow, I hope that kind of helped going through a couple of examples of looking at questions with regards to our two-sample hypothesis testing from a exam style question. Good luck.